Imagine a package the size of a sugar cube. No wires, no buttons, no mechanism of any kind, just sitting there. And it has enough energy to flatten every building in this city. Not a bomb, not nuclear, not chemical, just matter meeting its opposite. That opposite is called antimatter, and the terrifying thing isn't what it can do, it's that we already know how to make it. The question is, what's stopping us from making more? And what happens to everything we know about physics if we ever figure it out? To understand antimatter, you need to start with regular matter. The stuff you, this screen, this planet, and every star you've ever seen is made of. Matter is built from atoms. Atoms are built from smaller particles, protons, neutrons, and electrons. Each particle has properties: mass, charge, spin. An electron carries a negative charge. A proton carries positive. Now here's where physics gets strange. For every particle of matter in existence, there is a corresponding particle of antimatter, identical in almost every way, except its charge is perfectly flipped. The antimatter twin of an electron is called a positron. Same mass, same spin, positive charge. The antimatter twin of a proton is the antiproton. Same mass, negative charge. This wasn't a guess. It was a mathematical prediction made by a British physicist named Paul Dirac in 1928. He was solving an equation describing how electrons behave at high speeds. The math kept producing two solutions. One was the electron, the other was something that had never been seen, a mirror particle with opposite charge. People assumed he had made an error. 4 years later, in 1932, a physicist named Carl Anderson was studying cosmic rays, high-energy particles raining down from space, and his detector caught something extraordinary, a particle that moved exactly like an electron, but bent the wrong way in a magnetic field. Dirac hadn't made an error. He had mathematically predicted the existence of an entirely new class of matter before anyone had ever seen a single atom of it. Anderson called it the positron, the world's first confirmed antimatter particle. And with that single detection, physics was never the same again. Here's what happens when a particle of matter meets its antimatter twin. They don't collide, they don't bounce off each other, they annihilate completely, instantly, converting 100% of their combined mass into pure energy. No debris, no remnants, just a burst of gamma radiation and gone. Now let's put numbers to this because they are genuinely staggering. Einstein's equation, E equals mc squared, tells us that mass and energy are interchangeable and that the conversion rate is enormous. The c stands for the speed of light, 300 million meters per second, and you're squaring it. In nuclear fission, the process that powers atomic bombs, roughly 0.1% of mass gets converted to energy. In nuclear fusion, what powers the hydrogen bomb, it's around 0.7%. Antimatter annihilation, 100%. Every kilogram of mass on both sides, fully converted, nothing wasted. Run those numbers on just 1 gram of antimatter, half a gram of antimatter meeting half a gram of regular matter, and you release approximately 1.8 times 10 to the 14 joules of energy. That's roughly 43 kilotons of TNT. The bomb dropped on Hiroshima was 15 kilotons. 1 gram. The weight of a paperclip. So yes, the question of why we can't just manufacture more of this is a very important one. Here's the part of this story that doesn't get nearly enough attention. We do make antimatter, right now, today. The most famous place this happens is CERN, the European Organization for Nuclear Research, straddling the French-Swiss border, home of the Large Hadron Collider, the place that confirmed the existence of the Higgs boson in 2012. At CERN, physicists accelerate particles to nearly the speed of light and smash them together. In those collisions, the energy is so concentrated that it spontaneously creates matter-antimatter pairs, a particle and its antiparticle, born together in the same instant from pure energy. Scientists then use powerful magnetic fields to steer the antimatter away from it annihilates with the surrounding matter and trap it in a device called a penning trap, a magnetic bottle, invisible walls holding the most reactive substance in the universe. In 2016, CERN's ALPHA experiment held anti-hydrogen atoms stable for over 15 minutes. Scientists use this trapped antimatter to ask a beautiful question. Does anti-hydrogen behave exactly like regular hydrogen? Does it absorb light at the same frequencies? Does gravity pull on it the same way? These aren't idle questions. The answers could rewrite fundamental physics. But here's where the problem gets almost absurdly brutal. All of CERN's antimatter production across all its accelerators, all its experiments, running all year, adds up to roughly 10 nanograms per year. That is 0.0000001 grams per year. At that rate, producing 1 gram of antimatter would take approximately 100 million years. So we have a production problem. 3 brutal reasons. First, energy cost. To create antimatter, you need to smash particles together with enormous energy, and the efficiency is catastrophic. For every unit of antimatter produced, you've burned billions times more energy creating it. CERN estimates that manufacturing 1 gram of antihydrogen at current efficiency would cost approximately $25 billion just in electricity. Second, containment. Antimatter cannot touch any physical surface without instantly annihilating. That means you cannot store it in any container made of matter. You need continuous magnetic fields, invisible electromagnetic walls, to keep it suspended. One power interruption, one magnetic hiccup, and your antimatter is gone, converted instantly into a burst of gamma rays. And third, scale. Even our most powerful particle accelerators produce antimatter in quantities so small they are almost conceptual. Scaling that up isn't just an engineering problem, it may require entirely new physics we haven't discovered yet. Think about it this way. Making antimatter today is like trying to fill a swimming pool by collecting morning dew with a cotton ball, one molecule at a time, in a hurricane. We're working on it. Now here's the question that keeps cosmologists awake at 3 a.m. If matter and antimatter are always created in equal pairs, if every particle of matter born in a collision comes with a partner antiparticle, then when the Big Bang happened 13.8 billion years ago, it should have produced exactly equal amounts of both. Equal amounts, equal partners, which means they should have annihilated each other completely. Total destruction, a universe of pure light and nothing else. No stars, no galaxies, no planets, no life, no you, no me, no anything. But look around. Matter exists everywhere in overwhelming, unambiguous abundance. Somewhere in the first fraction of a second of the universe's existence, something tilted the scales. For every billion antiparticles created, there were 1,000,000,001 particles of matter. And after the Great Annihilation, that tiny imbalance, one particle in 1,000,000,000, survived to become every star, every galaxy, everything. This asymmetry between matter and antimatter is called CP violation, and it is one of the deepest unsolved problems in all of modern physics. We have detected small hints of it. We have built experiments specifically to look for it, but we have not yet found enough to explain the world we live in. The answer is out there, hiding in the mathematics of particles we are still learning to read. Despite all of this, antimatter isn't only a theoretical curiosity, it already saves lives. PET scans, used in hospitals worldwide every single day, work by detecting positrons, antimatter electrons. A radioactive tracer is injected into your body, it decays, and emits positrons, and the scanner detects the resulting annihilation energy to map your metabolism with extraordinary precision. Antimatter in medicine right now. And scientists dream of something larger, antimatter rockets, powered by the total conversion of mass to energy, would be, in theory, the most efficient propulsion system physically possible. Even milligrams of fuel could accelerate a spacecraft to a meaningful fraction of the speed of light. The physics works, the engineering does not. Yet. The universe knows how to make antimatter in enormous quantities. We're just trying to learn the recipe. Remember that package at the start? Sugar cube, no wires, sitting quietly on a table. It doesn't exist yet, not at that scale, not even close. But the physics is real. The particles are real. We live in a universe that almost wasn't, built from a 1 in a billion accident of broken symmetry, surrounded by the ghost of the cosmos that didn't survive. That's either the most terrifying thing you've ever heard, or